Hi, I'm Dr. Christopher Sutton. Welcome to my Introduction to GIS video series. In this video, we will discuss classifying map projections based on one of the biggest challenges we have in the map projection process: minimizing distortion. As I mentioned in the previous video, flattening a three-dimensional surface onto a two-dimensional plane results in the alteration of some properties of Earth's surface. There is no way to keep all the three-dimensional properties of Earth's surface intact on a two-dimensional surface. To understand map projection distortion, it is important to begin with two characteristics of longitude and latitude as they exist on the globe. First, longitude and latitude lines intersect at right angles. They do this everywhere throughout the globe. Secondly, meridians of longitude converge at the poles. When we create a map projection, we cannot maintain both of these properties at the same time. As a result, every map projection distorts at least 3 and sometimes 4 of the following properties: shape, size, distance, and direction. Projections that minimize shape distortions are called conformal or orthomorphic projections. In these projections, angular relationships seen in the globe remain accurate at all points on the projected map. In other words, latitude and longitude lines meet at right angles. While conformal projections preserve shape, they distort size. Why is this? While conformal map projections maintain the globe's perpendicular intersection of longitude and latitude, longitude lines on this map projection are parallel to each other and do not converge at the poles. In such projections, land masses may appear much larger or smaller than their true size. The distortion is most easily seen at the high latitudes, where the size of features like Greenland or Antarctica are dramatically larger than they would appear in reality. Why would we use conformal map projections? We use conformal projections in navigation and marine charts. Compass bearings remain accurate and course plotting is simplified. We use conformal projections in large-scale mapping when we are zoomed in on a localized area. We use them for property surveys and boundaries, engineering and construction projects, urban planning and design, as well as topographic mapping. And we use conformal projections where angular measurements are important, such as geological structure mapping, slope and aspect analysis, or wind direction studies. Here are some examples of conformal map projections. The most famous is the Mercator projection. Here we see meridians and parallels are straight lines that are perpendicular to each other. This map projection greatly distorts areas near the poles, but maintains shapes and angles. The Mercator projection is best used for navigation or mapping the equatorial regions. The Lambert conformal conic projection is one where we see meridians as straight lines converging at a common point and latitude lines being arcs of concentric circles. This example is the entire northern hemisphere. We most commonly see the Lambert conformal conic projection when we are zoomed in to a more localized area. For example, North America. Map projections that minimize size distortions are called equal area or equivalent projections. Equal area projections maintain correct area or size relationships between regions. A way of thinking about this is that a square kilometer in Norway is the same size on the map as a square kilometer in Brazil. While equal area projections maintain size relationships, they have considerable shape distortions, especially at the edges of the map. Why would we use an equal area projection? In some applications, preserving area is important when comparative analysis requires proportional representation. This is particularly the case in thematic mapping. Examples of equal area projections include the Malwide projection. Here we see latitude lines as straight and parallel, but longitude lines are elliptical arcs. The sinusoidal projection, which is best used in equatorial regions, like the Malwai projection, uses straight parallel latitude lines. Here we see the longitude lines are sine arcs, not elliptical arcs. The Albers equal area conic projection is commonly used in the mid-latitudes, particularly for the contiguous United States. For polar regions, we have the Lambert azimuthal equal area projection, where latitude lines are concentric circles, not parallel straight lines, and meridians are straight lines converging at a common point. In this example, the North Pole. Here is an example of the Lambert azimuthal equal area projection being used to map North America. At the beginning of the video, I introduced 4 kinds of distortion: shape, size, distance, and direction. More often than not, in our projects, we tend to choose between a conformal projection and an equivalent projection. We can think of conformality and equivalency as being at opposite ends of a seesaw, meaning that as you get better at preserving shape, you will get more distortion when it comes to size. When you are better at preserving size, you will get more distortion when it comes to shape. Conformality and equivalency cannot be maintained simultaneously. The most famous example of comparing a conformal projection to an equivalent projection is the comparison of the African continent and the island of Greenland. Recall that in a conformal projection, latitude lines are parallel to each other, longitude lines are parallel to each other, and latitude and longitude lines are perpendicular. The African continent straddles the equator, so we have less size distortion in the African continent. Greenland is located in the high latitudes. On the globe, longitude lines are closer together in high latitudes compared to the low latitudes. In a conformal projection, longitude lines are equally spaced and parallel. Thus, a conformal projection artificially increases the distance between longitude lines at the high latitudes. As a result, the African continent and Greenland are very similar to each other in size on a conformal map projection. In fact, Greenland is actually drawn slightly larger than the African continent. An equivalent projection maintains the size relationships between features. Here we can see the comparison of the African continent to the island of Greenland using an equivalent projection. Rather than being very similar in size, the African continent is nearly 14 times the size of Greenland, and we can see this much more clearly on an equivalent projection. Projections that maintain accurate distances are called equidistant projections. Equidistant projections maintain distances from a single point or along specific lines. Typically, an equidistant projection has accurate distances from the center of the map. These projections are useful for applications where accurate distance measurement is crucial over limited areas. Examples include broadcast signal coverage mapping, shipping distance calculations, response time mapping, and migration pattern analysis. Equidistant projections can but do not necessarily preserve shapes or areas. Here's the azimuthal equidistant projection, which preserves distance and direction from the center of the map. You may have encountered the azimuthal equidistant projection previously. Perhaps in this form right here, which if we add to it, and we'll add a background to display the flag of the United Nations. Finally, projections that maintain direction from a central point are called azimuthal projections. In azimuthal projections, great circle routes, which are the shortest distances between 2 points on a sphere, appear as straight lines from the map center. Angles measured from the map center are accurate, and these projections are best for areas immediately surrounding the central point, as distortion increases with map distance from the center. Examples of when direction matters include navigation, such as Great Circle route planning, bearing calculations, and polar navigation, military applications, such as artillery range and bearing, radar coverage maps and strategic planning, and communications like satellite coverage patterns, antenna orientation, and signal direction analysis. In the next video, we will discuss the various surfaces that are used to create map projections.